Friends, in last class we discussed about the different configurations of BJT. Then after we discuss about the common base configuration. In this we discuss the input and output characteristics of common base configuration. Today we discuss about the common emitter configuration, input output characteristics, and common collector input output characteristics. Common emitter configuration. In this configuration, so common node is emitter, input node is base, and output node is collector. So here we can observe the common emitter configuration of NPN and PNP transistors in this slide. Here we are applying the input between the base and emitter, and output taken from collector and emitter. And the input voltage in the CE configuration is base emitter voltage, it is VBE, and output voltage is collector to emitter voltage, it is VCE. And input current is base current, output current is IC. So we said the transistor main application is amplifier. To use this as an amplifier, we need to keep in active region. For that, emitter junction is in forward bias and collector junction is in reverse bias. So for NPN transistor, the negative terminal of the battery is connected to the emitter and positive terminal of the battery is connected to the P-type base. And similarly, the positive terminal of the battery is connected to the N-type collector and negative terminal of the battery is connected to the emitter. So collector junction is in reverse bias, emitter junction is in forward bias. Clear? So similarly you can observe in PNP also. Relationship between the common emitter. So we already know in common base configuration we seen that IC equals to alpha DC IE plus ICBO. So here alpha DC is the current application factor in common base configuration. Yes. From this we can write IC minus ICBO equals to alpha DC into IE. So by writing IE equals to what we can write, IE equals to IC by alpha DC minus ICBO by alpha DC, and we already know emitter current IE equals to IB plus IC. So from this we can write IC by alpha DC minus IC equals to IB plus ICBO by alpha DC. By taking the common as IC, we can write 1 by alpha DC minus 1 into IC equals to IB plus ICBO by alpha DC. So by writing IC equals to what we can write? Yeah, IC equals to alpha DC by 1 minus alpha DC into IB plus ICBO by 1 minus alpha DC. So here beta DC is the ratio of output current IC to the input current IB in CE configuration. So it is also called as current amplification factor in common emitter. In common base, current amplification factor is named as alpha DC. Here current amplification factor in common emitter is output current by input current. Here output current is IC and input current is IB. So IC by IB is also current amplification factor in the common emitter configuration. It is denoted with the beta DC. Sometimes it is beta. Yes, it is also denoted with the beta. So we can write beta DC equals to IC by IB. It is also equals to beta. So from this we can write IE equals to IC plus IB. So IB equals to IE minus IC. So now beta equals to IC by IE minus IC. So we can write beta equals to alpha by 1 minus alpha. Yes. So beta equals to alpha by 1 minus alpha. Now we can substitute this alpha by 1 minus alpha equals to beta in the above equation IC. So from this we can write what we can write, alpha equals to beta by 1 plus beta. Alpha equals to IC by IE, IE equals to IE plus I equals to IB plus IC, then alpha equals to beta by 1 plus beta. So the relationship between the alpha and beta is nothing but alpha equals to beta by 1 plus beta. Yes. So alpha is the current amplification factor in the common base, beta is the current amplification factor in the common emitter. Now we'll discuss about the input characteristics of common emitter. So we already know that input characteristics is always drawn between the input current and input voltage by considering the output voltage as constant. Here input voltage is VBE and input current is IB and output voltage is VCE. Now we are considering it as a constant. Yes. So you can observe the input characteristics of common emitter. So it is also looking like your common base input characteristics. Yes. So the input resistance is a change in the base to emitter voltage to the base current at constant VC. So we can write Ra equals to VB by IB when VC equals to constant. The input characteristics resembles the forward bias diode characteristics. So it is also looking like forward bias diode characteristics. After cutting voltage, the base current increases rapidly with small increase in the base emitter voltage. So by changing this VB value, small VB value, that IB value changes rapidly. So from this we can say the dynamic input resistance is small. Why? Because VB changes, IB also changes. Yes. So VB small change, that IB more changes. So from this resistance, input resistance Ra equals to delta VB by IB, that resistance, input resistance value will be very small. Yes. For fixed value of VB, IB decrease as VC is increased. And here VB and VC are positive for NPN transistor and they are negative for PNP transistors. Here next we'll discuss about the output characteristics. So it is always done between the output current and output voltage for the constant input current IB. So you can observe the output characteristics of transistor in CE configuration. So in this, the output dynamic resistance can be defined as change in the output voltage. It is nothing but output voltage is nothing but here VCE and output current is IC. Change in the output voltage to the change in the collector current IC for the constant IB. The output characteristics of CE consisting of again three regions. You can observe the three regions that are active, saturation and cutoff. So active region we already know, emitter and collector junction both are, emitter junction is in forward bias and collector junction is in reverse bias. In this collector current IC rise more sharply with increasing the VC. You can observe in the diagram. Yes. In linear region of output characteristics of C, you can observe in the active region, our collector current IC is more sharply increase with increasing the VCE value. In saturation region, we said emitter and collector both the junctions are in forward bias. Here IC does not depend upon the input current IB. The output current IC does not depend upon the input current IB. So this VCE sat usually ranges from 0.1 through 0.1 voltage to 0.3 volts. The cutoff region below IB. In this cutoff region, the emitter and collector junction both are in reverse bias. Here IB is almost 0. Yes. So the conditions for the saturation and active can say for cutoff IB equals 0 and for saturation IB is more greater than the IC beta DC. For active region VC is greater than the VCE set. This VCE set is generally 0.1 to 0.3 volts. Here DC current can be defined as beta DC, it is nothing but IC by IB. And similarly, AC current gain, it is nothing but beta AC. Change in the output current delta AC by change in the input current delta IB by considering the VC as constant. Next, we'll discuss about the common collector configuration. Here, collector is connected to the common node, and input terminal is base and output terminal is collector. So in this configuration, input is applied between the base and collector. Output is taken between the collector and emitter. Yes. So you can observe the common collector configuration of both NP and PNP transistors in this. Next, current relations in the common collector configuration. So we already know IE equals to IB plus IC. So we defined IC equals to alpha DC into IA plus ICBO. From this we can write IA into 1 minus alpha DC equals to IB plus ICBO. IA equals to, we can write IB by 1 minus alpha DC plus ICBO by 1 minus alpha DC. So we already defined that beta DC equals the relationship between the beta and alpha. So beta DC equals to alpha DC by 1 minus alpha DC. So by substituting these values, now we can get 1 plus alpha DC equals to 1 plus alpha DC by 1 minus alpha DC. So 1 plus beta can be written as 1 minus alpha. Yes. So I equals to, what we can write, 1 plus beta DC into IB plus 1 plus beta DC into ICBO. So ICBO is the reverse oscillation current, so we can neglect. Now IA equals to, what we can write, 1 plus beta DC into IB. So we define the current amplification factor in the common base as alpha, current amplification factor in the common emitter as beta, and now we are defining the current amplification factor or current gain in the common collector as gamma. So again, current gain or gamma is defined as ratio of output current by input current. Output current is nothing but here IA, input current is IA, so it is almost equals to the 1 plus alpha 1 plus beta DC. Yes, it is almost equals to the 1 by 1 minus alpha DC. Yes, so now we know the current gain in CC, CE, alpha, beta, gamma. Yes. Now input characteristics of common collector. So here it is graph between the input current IB versus input voltage VCB at constant VC. So the common collector input characteristics are quite different from the common base and common emitter. You can observe the input characteristics of common collector here. Yes, these are not looking like common base and common emitter. This difference is due to the fact the input voltage VCB is largely determined by level of collector to emitter voltage VCU. Yes. So here in CC, input junction base collector is reverse biased. Here input junction is base and collector. This reverse bias. So when collector junction is reverse bias, it offers the very high resistance. So very high resistance is present in the common collector. Due to this reason, the common collector input characteristics are differ from the common base and common emitter. Clear? Why? In previous, input junction is emitter. Here in common collector, input junction is collector. Yes. Due to this reason, it offers the high input impedance, and these characteristics in these input characteristics are differ from the common base and common emitter. Next, we'll discuss about the output characteristics of common collector. So it is the curve between the emitter current IE and collector current VC at constant input current IB. Since IC is approximately equal to the IE, here the common collector output characteristics are practically similar to the CE characteristics. So the CE configuration mostly used in amplification circuits because it provides the both voltage and current gain and it offers the high power gain. Why? Because in CE it provides the voltage gain and current gain. So ultimately, automatically it provides the high power gain V into I, and the CE compression can be cascaded in efficiently. Yes, that's why this common emitter configuration is more used in the amplifier circuits. Yes, clear? Here CC, this common collector is also called as emitter follower. Next, we'll discuss about the comparison between the common base, common emitter, and common collector configuration. So input resistance in the common base is very low and common collector is very high, and common emitter offers the moderate value. And output resistance, the common base offers the very high resistance and common collector offers the low, and common emitter offers the high or moderate value. Input current here IE in common base, IB in common emitter, in common collector IB. Output current in common emitter IC, in common emitter, in common base IC, in common emitter IC, and common collector in IE. Yes, here current again in common base alpha and common emitter beta and in common collector gamma. In common base, current gain is less than unity. In common emitter, high or moderate. In common collector, is very high. Voltage gain is medium in the common base and emitter also medium. In common collector, less than or unity. Yes. So in common emitter configuration is mostly used in the audio signal amplification, and common base is used as a input stage of multi-stage amplifiers. So when we are cascading the circuits, so this will be used as input stage. Cascade is nothing but by connecting the multiple amplifier circuits one by one. Yes, in this, in every circuit we require very low input resistance. So for due to this reason, this common base is used in the input stage of multi-stage amplifiers, and this common collector offers the high output impedance, low output impedance and high input impedance. So due to this reason, it is used in the impedance matching circuits. Here the voltage gain is also 1. So whatever we are given the voltage signal, that same will be almost same will be present at the output signal. Yes. So due to this common collector compression used in the impedance matching, and inputs common base is used as a input stage for the multi-stage amplifiers, and CE is used as a voltage and current amplifiers, as well as it can be used as a audio signal amplification. Yes, thank you.